assume that the both ship and model run in water of same density, the minor change in the density between fresh water which is in the model towing tank and that of the sea water are ignored, that is sea water density is it is 1.025 tons per meter cube and fresh water is 1 ton per meter cube approximately it is taken. So, that difference is ignored here and we consider it same density and at the same value of the fruit number, that is V square by GL we are just considering, it is a measure of some fruit number quantity. So, if you assume the ship and model meet the same fruit number, that is Fns is equal to Fnm. So, this quantity remains same, we assume it is the same for ship and model. From this relation we get, if we take this ratio Vs square by Vm square, that is equal to Ls by Lm, G is constant. So, that get and is equal to lambda. So, which obviously means that the velocity of ship and velocity of model or the square of that is related by lambda. So, from which you will get, we take the square root Vs by Vm, ratio of the ship speed to the model speed is equal to square root of Ls by Lm, which is square root of the model scale. So, which implies that if you run the model with the speed is equal to Vm is equal to Vs by square root of lambda, it satisfies this relation. That means the fruit number of the ship and fruit number of the model are same if the model is run at a speed equal to the speed of the ship divided by the square root of scale chosen for the model. The ratio of RRS, that is this resistance or residual resistance of the ship to the residual resistance of model. So, that is equal to Ls, we have seen it from the above, that is from here, from this ratio we know we are yes here from this you can put S in terms of L. So, we are just coming Ls square by Lm square into ratio of the speed. So, from this you can write it is equal to, you are using the scale here Vs by Vm is equal to this, or you can see that Vs square by Vm square is equal to lambda. So, this is equal to lambda lambda and this is equal to lambda square, which gives Ls cube by Lm cube, which is equal to lambda cube. Since it is Ls cube or length cube, it can be equal to the volume displacement, or since you assume same density, same as the mass displacement of the ship divided by mass displacement of the model. So, this is a relation, that is what implies is that if you know RRS, then you multiply RRS, if you know RRM, that is a model residual resistance, you multiply it by lambda cube to get the residual resistance of the ship. The same as you can know from this relation, these two, and this can take the ratio residual resistance of the ship divided by displacement of the ship is equal to residual resistance of the model by displacement of model. So, these things are known, delta S is known, delta M is known, RRM is measured from the model test when you run the model which follows this speed relation. So, from which you will be able to find out what is the residual resistance of the ship, and that means all the three quantities are known except this from which you estimate that. Here we are coming back to this term, which is one of the term which appeared in the parameters before, it is P by rho V square. So, here atmosphere pressure which acts in the ship and also in the case of a model. So, we ignore that, we take the same datum for the atmosphere pressure. Then here P refers to, this P refers to only to water head. If you are considering a point in the water inside the water domain, then this is the pressure relation, P refers to the water head. Thus, for a corresponding point in model and ship, if you are considering, then the P varies directly with lambda, because you know that pressure, if it is a static pressure water head, it is rho gh, rho and g are constant, and we assume it is rho and G are also same for Shipman model. So only variation is H. So for the model, so the pressure is related to the lambda, the corresponding point. So here you consider this, you are considering your ship quantity Ps by rho s Vs square divided by the model quantity, that is Pm by rho m into Vm square. So this is equal to, if it you can rewrite in this form, and we know that this quantity Vm square by Vs square is equal to 1 by lambda, and this pressure we have already explained here, this depends on lambda. So Ps by Pm is equal to lambda. So lambda divided by 1 by lambda is equal to, that is equal to 1. So that is this quantity P by rho v square will be the same for Shipman model, because Ps, you see this relation here, is equal to 1 means it remains same for Shipman model. So it is automatically satisfied. Now we look to other term. So first we know with the three terms considered, the functions of Froude number, Reynolds number, and the non-dimensional pressure, or called Euler's number. And we have seen the Euler's number is not significant, there is between Shipman model is same. So we have seen that ratio is equal to 1. Froude number, we have seen the Froude number, if it satisfies the model velocity, is equal to ship velocity divided by square root of lambda, the Froude number is satisfied. The third one what is left is the Reynolds number, which is VL by nu. So now here what we consider, body is deeply submerged, there is no wave making. So the initial case when we discuss about Froude number, we assume inviscid flow, so that we discarded or we ignored the Reynolds number, and we finally said it is only the wave making resistance or residual resistance important. Now we are saying that we are just considering the body is deeply submerged. When the body is deeply submerged, no waves are created, and only resistance available now for a deeply submerged body is a viscous effect, due to the viscous effect. So VL by nu governs the frictional resistance, which is a major component. Also it can refer to the viscous pressure resistance. So mainly the frictional resistance is considered here. So the frictional resistance Rf is now related to the Reynolds number. So when you say it is a double deep body deeply submerged, yes, okay, that is what I mean. So here, yeah, it is coming later, I think, about double hull. Frictional resistance coefficient Cf is equal to Rf frictional resistance divided by half rho Sv square. It is the same non-dimensionalization parameter here as we did before. To have the same Cf for Shipman model, the Reynolds number must be same, because the frictional resistance is dependent on Reynolds number, frictional resistance coefficient. So now we assume that nu s is equal to nu m. So here we say, just use the board, and here we assume if it is Rn s, that of the ship is equal to Rn of the model, that is Vs Ls by nu s is equal to Vm Lm by nu m, and now we assume nu s is equal to nu m, which implies that Vs Ls is equal to Vm Lm. So that is what is written here. So you get this relation here, Vs Ls is equal to Vm Lm. So from this we can write Vm is equal to Vs into Ls by Lm, and that is equal to lambda. So that is how you get this relation. So Vm is equal to Vs into lambda. So if you meet this relation, then you will be satisfying the Reynolds number between ship and model, that is the Reynolds number of ship is equal to Reynolds number of the model if the model is run with the speed equal to the ship speed into the model scale. So actually this is going to be different from the Froude condition, but still if you can meet this relation you can write. meet that requirement. Here what you do is this condition is quite different from the requirement of the wave making resistance similarity, because we have already seen the wave making similarity, that is CRS is equal to CRM when the Froude number of the ship is equal to Froude number of the model. So we have already seen that wave making resistance prediction from a model test matches between ship and model only when, that is you say the coefficient CRS is equal to CRM only when f Froude number of ship is equal to Froude number of model. So which implies that we have already seen that Vm is equal to Vs divided by square root of lambda. So here what you have, this relation is, if this is for the Reynolds number satisfaction, and here this is for the Froude number satisfying between the ship and model. So here we just seen that the Vm, the model speed need to be Vs into Ls by Lm, that is equal to Vs into lambda. So if you look to this, these two are not holding the same relation. If you run the model, it will satisfy one relation. If it is for the residual resistance estimation, the model has to run with this speed, or if it is for the frictional resistance estimation, you need to have a submerged body and it should run with this, the speed in relation to that. So when you usually do the frictional resistance, when you say it is a submerged body, deeply submerged, so suppose you consider this is the water level and the body is somewhere here, you consider this is a ship, it is deeply submerged, but since you cannot afford to have such a boundary beneath that, so what this is up to the load water line. So what you do is you put a double model, that is a concept used, just mirror image of that body. So you consider this, so you are putting two ships, this is the load water line, this refers to the load water line or the water line at which the ship. So you consider double model, this is called a double model, body is deeply submerged, so there is no wave making, and now the only effect is the viscous effect. So you run the model or tow the model at such a condition, then you get the viscous resistance. This is for two models, so you take half of it, half of the resistance, frictional resistance, you get the frictional resistance of the ship. So this is the concept used in the double model. So that is what say the condition is quite different, that is the relation what you have seen for Reynolds number satisfaction is different from the satisfaction of the Froude number between ship and model. So here if you look, if you use a smaller model, what is the scale, smaller model scale is high, lambda is high, so then the model speed will be higher. If you look to that relation here, if you look to this relation, if you go for a smaller model means lambda is high. So if you say it is a 1:50 is a model and 1:100, so the lambda will be higher for a smaller model, 100 for that. So Vm is equal to Vs into lambda. So when lambda is a higher value, Vm will be higher. So that is what it means, smaller model, higher model speed, which is difficult, you will see that from an example here, difficult to achieve. We consider a model of a ship having 150 meter long and 6 meter is the model size, model length. So here the ratio is 150 by 6, lambda is 25 and the ship speed is 20 knots, and that means 20 knots is the speed. So the model speed need to be ship speed into lambda. So 20 into 25, it comes to 500 knots. So the model has to be operated at 500 knots to match the Reynolds number between ship and model. So which is not achievable. 500 knot speed in lab in a towing tank is not achievable. So this is, it is not possible to satisfy the Reynolds number between ship and model in a lab condition. Another option is, you have to go for another options to have the same Reynolds number is to perform the model test in a superfluid. That is, you have to consider the relation between nu m and nu s, that is equal to lambda raised to 3 by 2. I think what you have to do is, if you consider this one, you consider the nu s by nu m is equal to Vs Ls by Vm into Lm. So that is equal to Vs by Vm. If you follow the Froude number case, it is going to be square root of lambda, this one Vs by Vm, and Ls by m is equal to lambda. So that is equal to lambda raised to 3 by 2. So that means if you consider that is nu s by nu m is going to be lambda raised to 3 by 2. So here nu s or nu m, that is a model, the fluid in which the model is tested is equal to nu s divided by lambda raised to 3 by 2. So that is how it is coming. So if there are two options of meeting the Reynolds number, one is increasing the speed, as I just increasing the speed of the model very high, or other option is you test the model, that is nu m represents the viscosity of the fluid in a model basin or model towing tank. The viscosity of the fluid is equal to the viscosity of the fluid in actual case, that is the seawater viscosity divided by lambda raised to 3 by 2. That means that is equal to for the example what we considered here, nu s by lambda is 25 raised to 3 by 2, or that is equal to nu s by 125. So you can meet a Reynolds number if you use a fluid in the lab condition which has a kinematic viscosity equal to 1 by 25th of that of the water, sea water, which there is no such fluid, and hence again meeting Reynolds number from that perspective is also not possible. So what it implies that whether these two options, running the model at very high speed or testing the model in a superfluid, these two options are practically not feasible, and hence meeting of Reynolds number between ship and model are not possible. So both the conditions of mechanical similarity cannot be satisfied in a single test. So here we have seen that there are two conditions, one is mechanical similitude, one is a dynamical similarity, and other one is a kinematical similarity. Dynamical similarity, here it is referring to the waymaking resistance, which shows the ratio of inertia force to gravitational force from which you get the Froude number. And other condition, second similarity, is the kinematical similarity, and which is represented by the Reynolds number, and that is represented by the ratio of inertia force to viscous force. So these two cannot be satisfied in a single test. We have already seen that velocity of model are totally different when you satisfy these two conditions, which is not possible. In the same run you will not be able to get to satisfy these two conditions. And other option may be, as I said, now using a superfluid, again such a fluid does not exist, so you cannot do it. Therefore deal with frictional resistance and waymaking resistance separately. So there is a easier way of, or practically acceptable way of treating the resistance prediction from model test to the prototype. So the total resistance coefficient Ct is equal to, you can split into the resistance coefficient Cr and plus the frictional resistance coefficient Cf. So that means the total resistance can be separated out as one as residuary resistance and other one as the frictional resistance. Now you know Ct, which is represented by total resistance by half rho Sv square, and that is equal to a function of root number, and here it is a function of Reynolds number. So you are separating it out like using the method of separation of variables. The function Ct is now represented by a function exclusively depending on root number and another function exclusively depending on Reynolds number. So this one will represent the frictional component and this one will represent the residuary components. So how do you predict the resistance using model test? So what you do is you run the model at the speed satisfying the relation. We have already seen that Froude number of ship is equal to Froude number of model. So you satisfy that, and we have already seen that the relation is you run the model at a speed is equal to the ship speed divided by square root of lambda, the scale of the model. So that is a relation. So you try to satisfy this, which is practically possible in a lab condition. When you run the model at that speed, you measure the total resistance of the model using a dynamometer or maybe using a load cell. You measure the total resistance of the model at different speeds. So calculate, now what you do is you calculate the frictional resistance of the model RFM using the flat plate formula, maybe ITTC formula you use. We have already discussed this before. What is the flat plate formula, what are the different formulae normally used, and how they are achieved, how the experiments are done, which we discussed before in one of the classes. So here ITTC, which has came out with a simple empirical relation to represent the frictional resistance coefficient, from which you will be able to find out the frictional resistance of the model. So we know that the frictional resistance ITTC formula, which gives the Cf value ITTC for Cf, it is given as 0.075 by log Rn minus 2 the whole square. So this is the ITTC formula for frictional resistance. So if you are using for Cf of ship, what you use is 0.075 divided by log Rn of ship minus 2 the whole square. So you get Cf as, or for this model you get 0.075 by log Rn of model minus 2. So only difference here is the Reynolds number. If you are using CFS, Reynolds number of the ship, if you are using CFM, so Reynolds number of the model should be used, and you know that Reynolds number of model and the ship are given by these relations. So once you know the velocity, length and kinematic viscosity of the ship, kinetic viscosity of ship means it is the sea water, then you will get Reynolds number of the ship, you substitute there, straight away get CFS, or if it is for the model here, use this relation. So that is how you find out the frictional resistance for this. So what you do is you measure the total resistance of the model, then you find out the resistance, frictional resistance of the model using ITTC formula. So here you use 0.075 divided by log Rn m minus 2 the whole square, that formula you use. Then find the model residuary resistance from that. So you know that the residuary resistance is the difference of the frictional resistance, the total resistance and the frictional resistance. So you get the residuary resistance of the model from that. The next step is we have already seen that the residuals of the ship RRS is equal to RRM into lambda cube. We have already proved that the same relation. Here you can see residual resistance of the ship divided by RRM is equal to lambda cube. So that is what we did here. So once you get that, you get RRS, that is residual resistance of the ship is equal to residual resistance of the model into cube of the scale chosen. So that means you have got RRS now. What you do is you estimate RFS, the residual resistance of the ship, as in step 3, that is you find out the Reynolds number of the ship, then use the IDTC formula 0.075 divided by log r n s minus 2 the whole square, which gives the residual CFS, and then CFS multiplied by half rho S V square, that gives the RFS. So that is the frictional resistance of the ship. Here only difference is you are using the ship dimensions LS, and here SS, that is half LS you use for the Reynolds number, SS for the resistance estimation of the ship. So now the total resistance of the ship is equal to RFS coming from here plus RRS coming from here. So you get both, you get the total resistance of the ship. So that means the total resistance of the ship is equal to RFS by RRS is equal to RFS plus, you can take the ratio of the densities of waters lambda rho, and the scale length scale lambda cube is coming from here, and RRM. So which is same as, you can just put this in this form, this into RRM is equal to RTM minus RFM. So just substituting for that. So the total resistance of the ship is estimated in this form. So to put it brief, in a model test, as we have seen, it is difficult to satisfy or not possible to satisfy Froude number and Reynolds number at the same time, and also it is difficult to, or just not possible to meet the Reynolds number between ship and model. What we do is we run the model which satisfies the Froude number, then get the total resistance of the model, and then you using IDTC formula find out the frictional resistance and take the difference, which gives the residual resistance. Once the residual resistance is obtained for the model, then you multiply it with lambda cube to get the residual resistance of the ship. Then subsequently what you do is you use the ship's Reynolds number and find out from IDTC formula the CF value for the ship and multiply it by the ship parameters to get the total resistance force of the frictional resistance of the ship. Now you just put it together to get the total resistance of the ship. So that is the procedure adopted in prediction of total resistance of a ship from a model test. So which implies that you cannot take a total resistance of the model, that is you can't just make a RTM from here, and you cannot just multiply by lambda cube to get the total resistance of the ship. So you have to follow this procedure, and finally you get the total resistance of the ship. Frictional resistance, we have already seen that unable to have same Reynolds number for ship and model, we have already discussed that. Hence we won't be able to obtain the frictional resistance from the model test. So thus use equivalent flat plate resistance, that is what we did in using IDTC formula. So use an equivalent flat plate resistance formula. Then the Froude assumed that a ship has a frictional resistance equal to that of a flat rectangular plate and having the same wetted area and the same length as the ship. So this, what they have considered is that the flat plate experiments which they carried out by Froude, they usually assume that the plate is having a length equal to that of the ship, and the surface area of the plate is equal to the mean girth of the ship, that is wetted girth of the ship. So that is how the experiments have been conducted, and from that only the IDTC formula or similar formula have evolved. So here the frictional resistance is given by this expression and here you can see that this depends on lambda t depends on the t and all that. This is a self explanatory ship length which is represented here, T is represented temperature, so viscosity variation due to temperature is there, wetter surface and ship speed is a V1 in meter per second, gamma is a specific weight of water. So, this is a relation where RF is dependent. The Froude assumption, when we split frictional resistance, Froude assumes the Froude assumption led to us to estimate the or splitting of total resistance into residuary resistance and frictional resistance. So, when it is done, the following things are ignored in that assumption. The fluid particles actual complicated path along the hull owing to the wave formed when the ship is moving. So, here we considered when the ship moves, waves are formed, the fluid particle path become maybe wavy in form, it is different from the case when it is having a free stream flow, that is in the submerged case when there is no wave. So, that path variation of the fluid particle is ignored in the case of this problem when you bifurcate the problem into residual resistance and frictional resistance. The speed variation of the fluid particle along the ship length owing to the hull form, here we used the flat plate formula, the water particle velocity around the flat plate and around the ship which is having a 3-dimensional form are different. So, when there is a curvature, there will be increase in water particle velocity which is ignored in this case in the assumption, because we are using a flat plate formula for the estimation of frictional resistance. Then the boundary layer, you can see the flow separation effects, the boundary layer formation around the plate and around the body around the ship are different, flow separations are different, the flow separation aspects are ignored, it is only the frictional resistance component considered. The difference in the boundary layer formation along the flat plate and ship, that is what I just mentioned. The boundary layer is going to be different around the plate and around the ship, that difference has been ignored. In spite of the above drawbacks, we have highlighted many drawbacks in the assumption of the Froude, where the split of total resistance to residuary and frictional resistance have been done. So, but in spite of all the above drawbacks, Froude's concept of splitting RT into RF and RR is still used in towing tanks. So, we are yet to find out a better method, better approach in predicting the total resistance from the model test. So, still we follow, in spite of all these drawbacks or limitations, we still continue to use the Froude's concept of estimating total resistance from the model tests conducted in a towing tank. Okay, this model tests are done. Now we have an idea how the model tests are done from model ship, and once you get the model test, how the model test results are extrapolated to the ship, what are the methods used, how it is done. There are a few methods which we go through. So, here this see that so, here with this model test and ship resistance prediction method, what are the methods which are used. Model test for ship resistance determination. The ship model is towed by the carriage at different speeds and the total longitudinal force acting on the model is measured. That is a way the model test is done, that is the ship model is there, it is ballasted to the required draft of the vessel. Then the model is towed with constant speed and you measure the force, longitudinal force coming to the model, or you find out what is the tension coming in the rope which is conducted or which is being used for towing the model at that speed. So, that gives that is the way you find out or measure the resistance of the model, or to measure the resistance here. The towing tank size, that is the breadth and depth, decides the size of the model that can be used. So, if it is a there is a restriction, you have to have the model size substantially smaller than the model breadth substantially smaller than the breadth of the tank or width of the tank, and the depth usually the experiments are done in shallow in deep water, and the water depth condition in a towing tank should be such a way that the water depth is sufficient in the tank so that the shallow water effects are not. So basically what it is looking to, the blockage effects not minimized, it is not happening there, you need to make ensure. The model is too wide, breadth is high, then there will be influence coming from the tank boundaries which will obviously increase the resistance and hence vitiate the results predicted from the model test. So that is a limitation of the model. So depending on the tank, and also the size of the model, when it increases, the forces coming on the model also increases. So the capacity of the load cell or dynamometer which you use also go high. So if you have a limitation on the availability of these equipments to measure the resistance, then that also put a constraint on the size of the model. The model should be manufactured to a high degree of finish. So model, we know that the three conditions which are to be satisfied in a ship model test are geometrical similarity, kinematical similarity and dynamical similarity. So one of the first and foremost thing is meeting the geometrical similarity. So it should be geometrically same. So that is why it says that model should be manufactured a high degree of finish, even a slight variation in the form of the model matters a lot on the prediction of the resistance test. We know that resistance prediction is lambda cube, and even a minor change in the form matters, that wrong results get predicted or get magnified by so many times, and the error when it comes to the ship will be too much. Then turbulent simulators are placed at the bow of the model to create a turbulent boundary layer over the hull. So we have already discussed about that. It is difficult to maintain the kinematical similarity because you are not in a position to satisfy the Reynolds number for ship and model. So but you know that Reynolds number of the model is very low compared to Reynolds number of the ship, and if the Reynolds number is less than 10 power 5, the flow is in the laminar region, or if the Reynolds number is more than 10 power 6, it is in the turbulent region. So generally for ships, the boundary layer around the ship is going to be turbulent because the Reynolds number is high. So when you do a model test, you would like to, even though it is not meeting the Reynolds number between ship and model, you would like to have a flow condition which is more similar to that around the ship, so that it is not only it is affecting the boundary layer, it also look into the effective hydrodynamic form of the ship. So in model test, turbulence is simulated. We have already discussed what are different types of turbulence simulators used, including net, sandpaper, tripwire and all that. So here in IIT Madras, we use generally a tripwire, and this tripwire, that also we discussed that even for a ship, the forward end of the flow at the forward end of the ship is generally laminar in nature, and so this tripwire is usually fitted maybe 5% aft from the fore end. So a tripwire is used, so that means the forward end, still the forward 5% of the length will still remain as laminar flow, and the one behind become turbulent when it crosses over the tripwire. So that is what is done here. Turbulent simulators are placed at the bow of the model to create a turbulent boundary layer over the hull. So next is the model is ballasted. You know that you put weights and there is a procedure involved in that. So you do that and see that the ballast, the model displaces as up to a water line as per the design load water line of the ship. So and also you should have the trim, if there is a ship is going to have a trim, the same trim also should be used for the model. the model is free to heave. We make the connection in such a way that when it moves forward, depending on the speed, the model may heave, it goes down, or it may pitch or trim. So this freedom should be allowed to the model, so that the actual operating situation will be created when the model test is also done. So this is a model setup for the resistance. You can see here you have the model, this is a model, and on the side of the model, okay, the model, the first it has to be immersed or ballasted to the required draft. So for which you can see the red items here, which are the weights which are placed inside the model to get the required displacement. So once you know the displacement of the ship, which you usually get from hydrostatics, you know what is the displacement as a design water line, and that divided by lambda cube will give you information about the displacement required for the model. So then you will come to know what is the total mass, in which you initially using a wave machine you weigh the model hull alone plus the fixtures and all that, then you find out what is additional weight, the red weights, or what is required to be put inside the model, and that also you measure and then you place it inside. So the total finally it will float at the design load water line. That is how the model is prepared. And here you have the there is a pivot joint here at this aft end, and there is a pivot joint at the forward end. These pivot joints gives freedom for the model to heave and pitch. That is the last point we discussed before. So this will give the freedom for heave and pitch or heave and trim, and so that is a condition for the model is prepared. Then you have a, you can see here is a brake pad and a brake coming here. There is a brake with a lever here up. So this can be, this is held at the required, held by the brake pad with the brake, it is held at a position, and the yellow structure here is a carriage of the towing tank, and the carriage is moved at the required speed. So here is another arrangement, you can see it is not, I think it is here, there is a tow point which usually coincides the center of the resistance. There is a tow point from which a rope goes through a pulley, and this pulley goes up and finally it is connected to a load cell. So when the ship moves at constant speed and when the brake is released, the tow rope is actually, that rope is pulling the model forward, and with that the carriage, when you operate the carriage at different speed, at each speed you find out what is the pull coming on this rope, which is measured through the load cell. So which gives the total resistance of the model. So that is how the model test is done. So I repeat, the model is made geometrically similar. In here we make this model using fiberglass, and there is a procedure adopted for the making of the model, where you get the form, maybe an AutoCAD drawing, from which you find out, you make a plug to the scale required, and scale is chosen in such a way that it should not have a wall effect, you try to avoid that, and even if there is a small wall effect you have to apply a correction for that, and then from the plug you make the mold of using fiberglass, and from the mold you make the model, and the model then you put stiffeners inside to retain the form and rigidity, and that model is one which is used here. Then you put the fixtures like what you see here for the pivot joint, and the two battens here for holding the brake, and that the brake is going up, and all this setup which I have already explained. So that is how the model test is done. So when you measure the resistance only when the model reaches a steady speed, because your resistance is for a particular speed. So there will be an acceleration phase for a carriage, and finally the deceleration phase. You do not measure resistance at that, or you do not use the data at that point, you use the data only when in the steady speed region of the test. So that is a setup which is used, and you can see that what I discussed, the rope is coming now, that tow rope which comes here goes through the pulley, it is a frictionless pulley, and which goes here. Here you see there is a load cell, and from the load cell it goes through the cables run from here to the data acquisition system here, and that the results are processed. You have all the controls for the carriage, everything here. So the carriage speed and braking, everything is controlled from here, and the data is fed in, and then the data can be processed in the data acquisition system, and from which the resistance is estimated. So this is the setup which you see above, and the previous one what you have seen is the below water portion. So this setup is what we have in here in IIT Madras to perform model test, and we have a towing tank of about 82 meter long and 3.2 meter wide and 2.5 meter water depth. So that is the size of the towing tank what we have, and the maximum speed of the carriage is achievable is 5 meter per second. So that is a system here which you for the prediction of how the model test to perform the ship model test. Okay, and maybe we continue in the next session, I think.